Alright, well, just toss those in for, give you a taste of what's coming. I hope some of you will be following me for years, although I do expect when I get up into the PhD level stuff, probably my audience will change somewhat. That's to be expected, I guess. Alright, well, back to the nitty-gritty. Now, the last time we found a matrix representation for the angular momentum operator LZ, right? And that matrix was a diagonal matrix, and that's to be expected. Without doing it explicitly, but I can show you why. I mean, instead of being L squared, imagine this is now just LZ, the Z component of the angular momentum operator, so LZ hat, okay? Now, these spherical harmonics, they are eigenfunctions of the two operators, L squared and LZ. So if you had LZ here, this LZ spherical harmonic, that's operator eigenfunction. That's the left-hand side of an eigenequation. Okay? So you could substitute in here the right-hand side of the eigenequation, and hence have m here, or m dashed, the eigenvalue times the eigenfunction. And the m dashed here, that's just a constant, so you can bring it outside the integral, and then you've got this spherical harmonic, this spherical harmonic. Well, these spherical harmonics, they are orthonormal, right? So the matrix element that corresponds to this will be 0 when m and m dashed are different, and non-zero when m and m dashed are the same. Well, that corresponds to a diagonal element, an element along the diagonal of the matrix. Okay? Well, it's a similar story with L squared, because remember that these spherical harmonics, they are the simultaneous eigenfunctions of two operators, L squared and LZ. That's how we found them in the first place, remember? So the matrix element that corresponds to this overlap integral, if you like, is also diagonal. Okay. Now, if you plug, I mean, there's two ways you can do it. You do it the hard way, the long way, which is this way. Now, I've written out this expression again. Had it several sessions back, where L squared is this complicated expression, which is a function of two polar angles, theta and phi, right? So you could plug that in, plug it in here. You have expressions for the spherical polars, spherical harmonics, and you can calculate this integral, and you will get something of this nature. You'll get this. Now, that's the hard way. The easy way is just to say that this is your operator, that's your eigenfunction. So the eigenvalues of L squared are L into L plus 1, right? And for L is 1, L into L plus 1 is 2. So your eigenvalues are 2h squared. So you get 2h squared and just 1, 1, 1 for each value of m, in fact. Right? So that's the easy way, just thinking in terms of using eigenvalues. Right? So it too, this with corresponding to this operator, the matrix representative, the equivalent matrix, if you like, that has the same commutation properties and so forth as this operator, that matrix will be diagonal. Right? Okay, now you have expressions for you have expressions involving theta and phi for the x component of the angular momentum, Lx. You have another expression from earlier lectures for L of y, the y component of the angular momentum, Ly. So you can put those angular momentum, Lx, Ly, here, and calculate what it is. And I ask you to do that for homework. It's a bit of work, and find the matrix representation of Lx is this, okay, and non-diagonal. And similarly for y, you'll get this with complex elements in the matrix. So I ask you to do that for homework. Now I'll say that again, just to help you with the homework. From earlier lectures, we had somewhat similar to this. We had an expression for the x component of L, hat. So Lx hat. We had another expression for Ly hat. Okay. So plug the Lx in here, or the Ly in here, calculate the whole thing. You have expressions for the spherical harmonics, for low L, so L is 1, 2, whatever. In this case just L1, and derive these. So do those for homework. Right? So doing that will help you. It's all part of the learning process, active learning. So here's the matrix representation for the operator Lx, and the matrix representation for the operator Ly. Okay, now they're not diagonal. Why is that? Well, actually this one is. Well, the diagonal matrix, you have to have zeros in the upper triangle and the lower triangle. So in this sense, these two are not diagonal matrices, and the reason for that is because the spherical harmonics here and here, they are not eigenfunctions of Lx hat or Ly hat. That's why the matrix representation is not diagonal. But these matrix, they are Hermitian. Okay. Now, just a bit of a lead into the next session. These matrices. So you've got. Now we did at the end of the previous section. We had a matrix representation for L of z. So you've got Lx, Ly now. So it's two more. You've got L of z from before. You've got L squared, which is this one. So you've got four of these matrices. You can then verify the commutation relations between Lx as a matrix, Ly. So square brackets Lx comma Ly. The commutation, the commutator. Okay, and you'll find if you put matrices into those commutators, the answer you'll get is the matrix equivalent, the matrix representation of what you got before when you're using operators. Right? So they behave in the same way. So you can either talk in terms of operators directly, or in terms of their matrix representations. And you have an infinite number of them, because then your L here can grow and grow and grow. And so the matrix that corresponds to this would be a square matrix of size 2L plus 1, corresponding to these different values that n can take. Right? I'll stop there and then head straight on into the next session.